All right, so I think we're recording. So this week is a Realm week. So we're going to be talking today about processors, tasks, and scheduling on processors, so folks can get a feel for how Realm manages the execution of tasks, and how scheduling happens inside of Realm. So the obvious place to start looking for this is at the spawn method. So I'm inside of processor.h here. And Realm has two different versions of spawning tasks, one with profiling requests and one without, but they're functionally equivalent other than that. And the idea is that, you're spawning a function and you give it, the way you name the function is with a task ID that you've previously registered with Realm. I'm not going to show you how the task registration happens here, but you have to, register, you're going to spawn the task with a task ID, you're going to pass in some arguments that you can pass as by value to that task, and you can give an event precondition and a potential priority, and Realm gives you back an event for when that task is actually done executing. So let's actually go take a look at how that's actually executed inside of Realm. So as with all things in Realm, we're going to jump into the processor impl file, which is where all the implementation details are for like the processor class. So if we search for spawn, we end up here. And what you see is that, the first thing that Realm does, right, is it, gets our singleton runtime, right, which we looked at the previous time for, looking at how we looked up events. There's also a similar data structure there for looking up processors. So I'm not going to show you how that works. You guys can go look at that, but it's equivalent to how you look up events. Effectively, we look at the processor ID and we can decode it and, get processors or get a processor implementation for this particular processor. Right, then we're going to make a finish event, right? And notice that, we always make this finish event on the node where the task is spawned from, right? So even if this task is going to ultimately execute on a remote node, right, the finish event for this task will actually be created on this node where the spawn operation was done, right? So we allocate a generational event for that. We get a new generational event. And then, we can get the current event associated with that particular, whatever the next generation is. And then we can actually, tell the processor to actually go spawn this task and give it the name of the finish event for this particular task we're doing. And then we can return right away, right? So, and then we return the event back to the user when we're done. So let's actually go look at this spawn task call and see where that goes to. I'm going to ignore that one. We'll come to that one. So the first, actually, let's do this one first. So one of the first things that can happen, this spawn task is actually a virtual method dispatch on a processor implementation kind. So if I actually pull up the declaration of that processor impl class that we saw that we're dispatching on, that's actually a pure virtual interface. And if I look for proc imp, here we go. Right, so effectively this processor impl interface here, right, is how there's a bunch of virtual methods on here, and here's the spawn task one that we're actually looking at right now. But effectively, it defines an interface for all processor implementations. And what you'll see is that there are several different incarnations of this processor impl interface, one for like local processors, one for representing remote processors, one for representing processor groups, and so forth. And we'll look at least the remote and local ones today. And you can go look at some of the other ones. But this just gives you a generic interface for all the processor implementations that you might have to have inside of Realm. So let's actually look at the remote processor version of the spawn first, because this is actually the one that will actually send the task to a remote node. Right, so we get in all of our arguments, including our finish event. Right, and if we dispatch into this remote processor, what that means is that effectively the processor that the task was spawned on is actually remote from the node that we're currently on. So what we're going to need to do is to pack up all the data for this task and ship it over to the node where it's actually going to execute, and then we can actually execute it over there. So there's a bunch of details here for handling really large argument sizes. Right, effectively, if these args are bigger than a certain size, Realm will actually have to, package that up into multiple active messages. right? And that's what this fragment payload is needed is happening. Effectively, it's breaking up this payload into multiple active messages to send over to the remote node. But in the common case where these args are actually pretty small, you can send this all with just a single active message, and be done with it. Now, the active message that we're sending is one of these spawn task active messages, right? And so effectively, you're packaging up this active message, setting all the values, and then when you call active message commit, that sticks the active message into the network, and eventually it'll run over on the remote node where you've sent it off to. So if you actually look at this spawn task message here, let's see, did I spell that correctly? No, I'm typing vim commands here, forgetting that I'm in a browser. Right, so here's our handle message functions. This is the static method that gets called when the active message arrives on the remote side. And you'll see it actually does something very similar to what the spawn task does, right? It gets our processor implementation, right? It unpacks the message. If we're doing the multi-message send for large payloads, right, we have to kind of reassemble into the buffer, and I'm not going to talk about how that happens. You can go kind of work that code on your own if you want. But the common case is you get the full implementation. At this point, you've actually got your full task available to you by the time you get down here. And then you can effectively get the corresponding generational event for the finish event here on this local node. And then you can call spawn task again, right? This again dispatches through that virtual function interface, except this time instead of being on a remote processor, we're going to end up on a local processor, right? And that's what's going to actually allow us to actually do the work locally to actually spawn this task, right? So if we come back to spawn task here on the local processor, okay. So now we've done any work we've needed to do to dispatch the task to a remote node. Now we're on the local task version of this, right? And effectively we're calling spawn task again, but now we're local to the node where the processor lives, and so we can actually do all the work here to actually execute this task. So the first thing we're going to do is we're going to make a task object. And so a task object, actually, if we pull up the tasks.h header file here, this task object is effectively just a structure which is going to hold a bunch of data associated with what we need to actually execute this task, right? So it's going to have the name of the processor that's task going to execute on, the name of the function ID for it, pointer to the buffer for the data, the buffer length, priorities, before and after events, like all the standard things that you might expect to see on this task. One little digression that's worth pointing out here is that this task is actually an instance of a more general base class, which is called an operation. And similar to how Legion has operations, Realm also has operations. Realm's operations also abstract, the concept of stages that that the operation goes through during its execution. So we're going to do a brief little digression here just to look at that. I'm not going to look at any implementation today, but I just want to show you the interface, and so you can see what the stages that a task is going to end up going through as it executes. You can see the virtual methods here that that task is implementing here in terms of operation. But let me actually just show you the base operation class here. Right. So here is the base operation class, and what you'll see is that effectively there are a couple of stages that an operation goes through, right? So the first one is marking it ready, right? Effectively, once the event precondition has been satisfied, you can actually be ready to execute this thing, right? And effectively, this can also deal with cancellation and stuff like that. Like you wouldn't call this, right, if it's been canceled, which happens when you get a poisoned event and stuff like that. Marking started means you've actually started executing this. So this is the event precondition has been satisfied. This is it's actually started running, right? And then marking finished, right, is actually saying when you're done execution, right? Termination means you weren't poisoned also. And you notice that you can also attempt to cancel in the cases where poisoning has come through and stuff like that. You can set priorities. And there's some general printing functionality for debugging and stuff like that. There are other kinds of operations in Realm, such as dependent partitioning operations or copies, and we'll look at those at a later point in time. But for today, we're going to focus on the task version of this. So I'll pop back here to task.h. And so, this task is an instance of an operation. Realm does track all of the operations in a special operation table, which is probably something else that we'll look at a future point in time. But for now, we're just gonna deal with the task version of this. Okay, so let's pop the stack a little bit here. Right, so effectively we make one of these task objects. You can just allocate that on the heap, right? I mentioned that all operations get tracked in an operation table. Effectively all the operations that are in flight on this local node. And so you can see we're queuing this task into that operation table there with this particular function call here. And it effectively tells you, what's the finish event for this particular task, and saying what the operation is associated with that event. And then we call this enqueue or defer task method here. So let's go take a look at where that goes. Okay, so there's a bunch of stuff happening here. We'll come back to this very simple case where there is no precondition, because the enqueue task is actually the most interesting thing to look at here. But before we can do that, let's actually talk about the case where there actually is a precondition event for running this task. Right, so if there is a precondition for running this task, we can look up the event implementation for this, right? So again, you can get the runtime singleton, get the event implementation, right? Get the start generation for it. You can test whether or not it is triggered. For now, let's assume that it hasn't triggered. Realm actually maintains a cache in this processor implementation to see if there's any prior tasks that have also waited on this particular event. And so what this cache lookup is doing is effectively saying, like, are there any other tasks that are also already waiting on this event? And if so, I can effectively add this new task to the set of waiters or to that waiting entry for that particular event. So we're going to skip the cache case because it's complicated. There's lots of stuff happening, but conceptually what it's doing is just like deduplicating if multiple tasks are waiting on the same event precondition, which tends to happen pretty frequently. You can often, deduplicate their weights on that particular event. So let's actually look at the case. Let me make sure I can find the case here where we actually weren't actually hitting in the cache. Let's see. Make sure I find it here. Right. So if we didn't hit in the cache, we have to go into this deferred spawn operation. And so if you look at this deferred spawn, which I think is over here. Yeah, here it is. Here's your deferred spawn method on the task. So just so you see what I'm doing here. So you see this task error deferred spawns. This is a member variable of the task class, right? And we're going to call defer, right? And we're giving it the generational event implementation for the starting method and the generation for it. And if we come over here to the task class, right? You see deferred spawn is a member of this particular task, right? And what it is it's one of these event waiter classes. So if you remember from our previous lecture on events, right, there was sort of a generic interface for waiting on events, right? And you can see that this deferred spawn class is an implementation of that event waiter interface. And so what this defer method does, let me see if I can actually find it over here. Let's look for deferred spawn wait. I thought it was over here. Maybe it's in the implementation class. Maybe it's in tasks. Oh, it might be in task.cc. Let's try that. Let's see here. Here we go. Okay, right. And so effectively, this task deferred spawn defer event, right? It just sets itself up. If it's not in the list of pending waiters for this particular event, that's part of the cache over here. But really the interesting thing here is it calls wait impl, which is the base event implementation class, right? And it says add waiter, right? And it gives it the generation that it needs to wait for, and this is the name of the the object that's waiting on it, right? And effectively that will cause this task to not be executed until this event triggers, right? So effectively this enqueues this deferred spawn thing as a thunk to actually trigger once the event has triggered, right? And we looked at this code last time, so I'm not going to actually show you, what add waiter does, but you can go look over the event implementation class and see how it gets added to the list of things to trigger once the event generation triggers that we're waiting on. Right, and when that happens, right, we get this callback when the event actually is ready. Right, we get the callback telling us what's happened. If we're poisoned, we're going to go through the whole cancellation path. We're not going to look at that today. But if we weren't poisoned, which is the common case, right, then we're going to go back to the processor implementation and call enqueue task, with the list of tasks that have potentially been added. And that's effectively equivalent to if we're back here in enqueue or deferred task, right, calling enqueue task. So effectively it's going to do the same thing and go to the same place, right? Like, so once you've had your event precondition, satisfied, that's how you get the callback to actually start running the task. So it's worth pointing out, that deferred spawn thunk that got made, right? That's a little dynamic allocation that gets made on the heap. And one thing that Realm does a lot of today is it does a lot of those creation of thunks on the heap, right? Now, this is slightly better than, like, it used to be the case that this deferred spawn member was actually its own thing on the heap, but now it's a member variable of the task, so it's just kind of part of the task operation itself. So it's a little bit better, memory usage and not segmenting the heap and bang on the malloc and free implementation quite as much. But your task is still living on the heap and stuff and sort of maintaining its own state for deferred execution. Okay. All right, so, once the event precondition has triggered, either because there was none in the beginning or because we got the callback coming back from the deferred spawn waiter, right, then we can go look at this enqueue task here. Let's see if I can type. That's the processor group one. I'm going to try to notice you should never call those on the remote processors. Let's actually look at the local processor enqueue task here. Right, you notice you can either enqueue one task or enqueue multiple tasks. They're effectively equivalent. We're both going to put them on this task queue thing. So let's actually look at that task, what that task queue thing is. So if I'm over here let's actually open up, we'll pull up proc impl over here in a new window just to make sure that we keep some of our state around and won't have to switch back and forth. Okay, well actually we're going to want to be on the local processor. So here's the local task processor, which this is the implementation of the processor interface for all of our local things, right? Or for all of our local processors. And what was I trying to show you? What was it called? It was the task queue. Right, so we have a task queue. So this task queue is the list of all of our tasks that are ready to execute, which means they have had all of their preconditions satisfied. And if we actually find this task queue thing, I think it's over here in task.h. Yep. Okay, so this task queue is effectively a priority queue. What it does is it maintains a list of the ready tasks sorted in the order of their priorities, right? So tasks can have different priorities, right? And effectively you need to make sure that, we run the highest priority ready ones ahead of the lower priority ones, right? And so the things at the front of the queue are the highest priority tasks that are ready to execute, and the ones that are at the back are the lowest priority tasks that are ready to execute. One thing that you'll notice is that this doesn't take into account, right? It's only tasks that are ready to execute that are in this list, right? And so the things that, tasks that haven't had their precondition satisfied are not visible to this part of the scheduler, right? And that's important because some people are surprised. They expect Realm to do something clever and maybe not execute ready tasks because, there's some higher priority tasks that hasn't had its precondition triggered, but it's about to be triggered. Right, we don't do any kind of delayed execution to account for those kinds of cases. Realm will eagerly execute tasks as soon as they're ready, and then but it won't preempt a lower priority task that's already running from if a higher priority task suddenly shows up because it's had its event precondition satisfied. So anyway, just keep that in mind when you're looking at these these ready task lists, right? And so we can actually now go look at enqueue task. In here, if I can type correctly. right? So when you add a task to the task queue, right, what this is going to do is it's going to mark this task as being ready to execute. So that's one of those operation calls to effectively tell the operation, like, effectively this task is ready to execute. If it's been, if you call mark ready and this operation has been canceled, right, this will actually return false, right, and that's effectively, that will push you down into this mark finish path. That's effectively like the task was poisoned before it could actually become ready to execute, right? And so that's what's going on in this particular path. But the common case is to come down this particular path here, right? So we take the lock, we add it to the ready task list, and then what we have to do is we effectively have to tell anybody who's looking at this task queue, and we'll talk about who these callbacks are that are looking at this task queue in just a minute. We have to tell them that there's now a task in this task queue in cases where, like, this task queue was previously empty or didn't have anything in it. And the reason for that is that effectively this is how the task is ultimately going to end up being run. And we're going to see is there's sort of like, a thread pool for most of these processors that's actually going to come through and execute these tasks. So you have to tell those thread pools that there's actually work available in this task queue, if they're not already, up and pulling tasks off of this task queue. And that's what these callbacks are going to help facilitate. And so we'll take a look at how that works here in just a minute. But effectively, all you have to do is really just take the lock, put it in the queue, and then if necessary, wake somebody up to tell them, hey, there's work available in this task queue for us to actually go do stuff. Right, and the enqueue task version of this with multiple tasks is very similar. It's just doing stuff with n things instead of just one thing. And so, you guys can come in and take a look at that part separately. But conceptually, it's doing the same thing. Okay, so how do things actually get pulled out of this? So we've got this task enqueued now. Effectively, we've had its ready precondition event triggered. It's gone through all the steps. It's got added to the ready queue for this particular task queue for a particular processor. How do we know that this task is actually, how is it actually going to get run? Well, for that, we're going to have to come back and take a step back and actually look at how the processor implementations actually work. So let's actually, let's find let me pull this over here. Let's actually look at the processor improl, the local processor improl class again. Or actually, we'll look at the processor improl interface, and then we'll talk about, how it's actually implemented in the local case. So most processors actually have a queue of worker threads associated with them to actually, or I should say a pool of threads associated with them to actually execute them, right? And this is true of, pretty much every kind of processor that the Realm has. Every processor has its own thread pool, which may be one or more threads to actually go through and do stuff, right? And Realm, on the process of creating a processor, right, we'll call the start threads for each of the processor things to tell them to spin up, and then tell them, when Realm is shutting down, to shut themselves down nice and cleanly. And then there's also support, for adding processors to group processors and stuff, which I don't think we're going to look at today. But effectively, like these two methods here, are used for managing like the thread pool for running, a specific processor, right? So if we actually look at like the local processor impl, right, they have an implementation of start threads and shutdown. So let's actually take a look at what these methods do here to actually spin up the thread pools to actually run tasks. So if we look at local task processor here and start threads, right? So it's going to dispatch onto this scheduler, right? Which is actually going to be the thing that's actually going to spin up the thread pool and actually, run the scheduling for this particular local task processor. So if we go back here and actually look at this scheduler, you can see this is a member of this local task processor class here, this threaded task scheduler. And if we look at that, one thing you might find a little bit surprising that this is actually also a virtual class. Let's see if I can find it here. Oh, it might be over in task.h, I think. Yep. So, this threaded task scheduler, right, is an instance of a thread scheduler. And thread scheduler is actually an even more general class in Realm, which you'll see like there are other worker pools of stuff like for the background worker threads and things that we'll go look at some point later. But this threaded task scheduler is actually specific for executing tasks. So it's a specialization of the thread scheduler for running tasks. So there's a bunch of methods in here for starting and shutting down and stuff very similar to what you see on the processors. This thread scheduler thing will also get used for background worker threads and stuff like that. But now we're also going to have some additional pure virtual methods as part of our interface here for executing tasks, right? So this is a specialization for a group of threads that are actually going to go and execute tasks. And we'll actually look at some of these here, but let's actually look at the two different instantiations of this class that are interesting to Realm. So there are two particular ones. So if I search for public threaded task scheduler, we're going to see that there are two versions of this that are worth looking at. So the first one is this kernel thread scheduler, right? And you can see here the comment, right? Effectively, this version is going to use one kernel thread for executing every single task that has to be, live at a given point in time. And so this is actually the version of the threaded task scheduler that gets used when you pass in the -ll kthreads command line flag to Realm today, right? Effectively, it says to Realm, please execute every single one of these tasks, right, on its own kernel thread separate from any other tasks, right? And we'll take a look at how that's implemented in just a minute. But there's also a second version of this, threaded task scheduler class here, and this is the one that's more commonly used for performance, which is the user threaded task scheduler, right? And so what this one does is it will have a smaller collection of or a much smaller thread pool, most likely, right? Because you don't have to share. You can actually share the same kernel thread across multiple live executing threads. Because like if you preempt a task by waiting on an event, right? This version will actually context switch or effectively swap the stack off of the thread and then put a new stack on the thread and then use the same kernel thread to execute the next task, right? And so this one is often much more efficient. Right, it doesn't have to go through like OS context switches and stuff as much, and so it will do its own user level thread switching, for each individual task it's going to need to execute. Right, so we'll look at these two, but they're both instantiations of this this task scheduler class, right, which is being used. Where did processor impl go? Or local tasks. Here we go. They're both instances of this threaded task scheduler, right, which you can instantiate any of the local processor impls with, right, and actually use that for executing tasks. Okay. Right, so effectively calling start here is just going to start up whatever task scheduler you've actually instantiated your local task processor with. And you can actually see, if we actually look at let's see if I can, actually, what I probably want is local. Right. So actually here you can see the in the creation of your like for example local CPU processor, you can actually see the ifdef here, right? Checking to see whether we've been told to use the kthreads version. If not, we're going to use the user level threading scheduler, right? Otherwise, we make a kernel thread scheduler and set the scheduler, with the number with the configuration, right? And so the kernel thread one starts with 3 default threads, whereas this one's probably just going to start with just a single thread, right? So that's exactly where these schedulers get made as part of the construction of these processor kinds, right? And then they get started when they're told to start. So let's actually go take a look at let's see here. Let's actually look at kernel thread scheduler here, right? And what this is going to do, when you start up, let's just say we take a look at the kernel threads task or kernel thread task scheduler, right? The first thing it's going to do is, when you tell it to start, it's going to spin up, a bunch of these workers, right? So you can call this worker create method. And this is just going to make a thread and start it running, and then, send it into sleep mode. And we'll actually go take a look at this, these scheduler loops and stuff in just a minute to see what these threads are actually doing. I'm going to say now, Realm has an abstraction for a thread class, and you can find that in thread.h. We're not actually going to go look at that today, But effectively, Realm's sort of generic abstraction over top of threads that work for POSIX threads and Windows threads and all those other things, right? Because Realm has to run on top of Windows also, right? So this thread is just sort of a generic abstraction on top of things. Actually, let me just show you the interface for that, because I think we will see some of the other API calls for that showing up over here, just so you know where to. Oh, and apparently I can't. Maybe it's threads.h. There we go. Right. So there is a generic thread class over here. It effectively abstracts over all the kinds of threads, as I said, and it has a bunch of operations that can be associated with things you can do on this particular thread, like running operations and stuff like that. And here's our generic thread scheduler class that you can also come look at. So anyway, that's a little bit of detail. I think the methods that I want you to see actually are over here in this thread scheduler class that I think we'll actually see are these sort of notifications to the thread scheduler about a particular thread, starting, blocking, terminating, right? All the kinds of things that, are being ready to run, right? Those are all things that the thread scheduler wants to know about. And we're going to see some of these API calls here get used a little bit later here shortly. So anyway, just want to show you guys those in advance so you know that know where the context is for them when we encounter them. Okay, so I showed you how the kernel thread scheduler works. We're going to go look at what these threads actually do once they start running. But let me just briefly show you the user thread scheduler does something similar. The only difference is that it's only going to start a small number of threads here. Also, doing slightly different loop than the ones that than the kernel threads versions, but effectively doing something similar. And there's also the same shutdown methods and stuff like that for cleaning up all the threads when we're done running Realm and stuff. Okay, let's actually take a look at what these threads actually do once they get started up, so that you can have some context of how they're actually going to go start pulling tasks from that ready queue to actually start executing them. Let's actually take a look at this host thread loop. This is the one that I want. Let's actually do the kernel one because I think it's actually easier to understand.
Why would you need more than one kernel thread to do the user?
Right. So for the user thread ones, so in general, I don't think that you need more than one thread. With some of the I/O processors, you might have more than one, right? Because you can most Realm processors only allow one task executing at a time on the processor, right? But some processors, like the I/O processors, actually allow you to execute multiple tasks in parallel on the same processor at the same time, with the anticipation that they're going to block on stuff that Realm doesn't have any control over, like I/O operations and stuff like that, right? But in general, I think you only really need one thread for the user thread task scheduler. Let me just see if that's right. So you see the default number of threads here is 1, right? On this user threaded task scheduler. We might need to ask Sean why he would ever configure that to be more than 1. I'm just reading the comments here.
There's I/O processors, right?
That's why I was thinking is I/O processors would be the obvious ones to do that with. But I'm trying to see if I can think of a reason that you would need it on like a normal CPU processor. Yeah, I think active, right? So yeah, it's however many active slots you can have for executing tasks, which for most Realm processors is just 1, right? So, yep. Okay, hopefully that answers the question. Yep. So if we go back to kernel thread task scheduler, start. Oh yeah, and we go to worker create. Right, then these threads start running the scheduler loop with lock. Right, which just calls scheduler loop while holding the lock. Okay. All right. So this is a big, complicated method. But this is effectively like the main scheduler loop for these threaded task schedulers, right? So these are the things that all these threads are going to run to actually try to execute tasks, right? And you see they're just effectively going to spin for forever, right? They're going to get preempted when they're not doing stuff, and then they're going to pull tasks out. So let's actually try to, this method is pretty complicated. I'm going to try to give you a flavor for what's happening so that we can actually see like where we pull tasks off and then how we actually run them. And I'm going to be. I looked at this earlier today, but it's so complicated that it always pops out of my head. So bear with me as we work through this method a little bit, right? Okay, so the first thing we're gonna do is like check for any internal tasks. Realm does have a concept of running internal tasks. They're pretty rare, and I think we've actually mostly gotten rid of some of the concept of internal tasks. But I'll need to check with Sean on that. But this block of code through here is just handling internal tasks, and for the most part, we can pretty much ignore that because we're interested in the case we're actually running real application tasks. Right. Okay. So, Realm will often have, a particular processor might have multiple different tasks executing concurrently, right? But only one of them can be actually executing at a time. The other ones are preempted, right? And so the first thing we want to do is like check to see if there are any tasks that we're running that got preempted because they like waited on an event. Then we want to resume those before we start running any new tasks. Effectively, we give we give tasks that we're already executing priority because we want to make sure that they make progress and drain out of the queue over starting new tasks. Now, there is a way for users to actually modify priorities to make sure that like new tasks can actually have an even higher priority than resumable tasks. But in general, by default, sort of the default for Realm is always, if a task has actually started running, even if it's a low priority one, we kind of want to allow it to drain off before we actually start a new task, right? And so, if there's a resumable task, you want to check to see if there's like the priority for that, right? And if so, try to get that task off of the task queue. Remember, I said the task queue is kind of like a priority queue, right? And so, like, that's effectively what's happening here. We're either, getting the most recent, resumable task off the task queue, which would be right at the front, right? Or we're getting like a new task that hasn't started running yet, right? Now, if we did get a task to actually execute, right? Now we need to make sure that we wake up, right? A worker thread to actually go and do the work to actually run this task, right? We may need to, create a new worker if all of like say for example, if we're running in the kernel thread version, right? We may need to actually, create a new thread because like all of our existing threads are already occupied with tasks that we're running, but then they all got preempted, right? So you may have to create one, or you could like, make sure that there's some worker task here available to actually run this task. Okay. We may need to update priorities on the threads, right, in order to enable them to actually, like give higher priority to the thread that's actually running this new task, based on the priority the task asked for. Let's see. I will need to ask Sean what these context managers are. I have not figured them out yet. So TBD to figure out what these are, but they actually don't matter so much for actually running. I actually think these have to do with the CUDA contexts and stuff. So like if you have like an accelerator, what I think these are, I'll give you my theory, and we can confirm this with Sean. But for processors that have contexts, like say like a GPU processor that needs to have a CUDA context associated with it, or like a HIP processor or something that also needs to have a context associated with it. These context managers are making sure that there is a context that's actually bound to this thread for actually executing this particular task, right? And making sure there's references associated that the task, these contexts, can refer to the task and so forth. Not all processors obviously need to have this, right? Like normal CPU processors, they're just going to just call like a function pointer, don't need to have this. But if you do need to have one, then this is the stage where you have to make sure your contexts are set up before you actually run this task. Okay. Let's see. And if so, let's see. I think if we've got this, this is actually. Let's see. I'm trying to remember what. Oh yeah, here's the execute task call. Right. Okay. So if we did get a task, right, then we can actually do the execution for this task, and we'll go look at that in just a second here. There are also cases down here, right, where we might have, if we didn't find a task to actually run, right, we may need to signal to other threads that had tasks that were, preempted, but were waiting to work, to actually wake them up to start running, right, if we didn't actually find a new task to run. Right, and then down here we have the shutdown conditions where we're checking for like, should we exit out of our while true loop, and if not, like there are modes to go into sleep and stuff down here, right, to effectively put ourselves to sleep until there's actually work to do, to make sure that we don't keep spinning forever and burning cycles and power and other stuff, and so this is effectively the sleeping waiting condition for new tasks to show up. Okay, so let's actually go look at this execute task call, because that's actually where we're going to go, we got our task, we pulled it off of the task queue to actually go execute it, and let's actually see what happens. And so you see both of these are actually pretty much the same for both the kernel and the user thread scheduler. We could probably actually pull that into the just the generic threaded task scheduler, since they're both the same. What they do is they talk to the task and say, go execute yourself on this particular processor that you're associated with, right? Okay, so we can go look in tasks.c, or we can actually look for execute on processor, right? And so this is the stage where, we're actually gonna start running this task on this particular processor. We check to make sure that we've got our processor assigned. If we have any profiling measurements, right, we're going to do some work to record, like if the user asked for us to tell it which processor it actually ran on, right, we're recording profiling measurements, right? We get our thread, we tell this thread we're starting this particular operation, this particular task that we're going to be executing, telling the thread which operation it's running, right? We can start any kind of performance counters associated with the measurements that the user asked us to do. So like, if your user asked you to measure, the number of, loads and stores that occurred inside of this task, right, those all get counted up here by, telling the thread to start measuring certain performance counters associated with the profiling requests that the user asked for, right? We can call mark started, which is one of those operation calls to actually say we're starting to run this task, right? And assuming we weren't canceled, right? Mark started can also return false in the case where this task was canceled because it's, got poisoned or something, or canceled explicitly, right? But in general, we're almost always going to be in this okay to run mode. We can effectively set there's some thread local variables that we often set, inside of Realm to configure this task. So this is saying, what our current processor is the processor that we're executing on. Here's some more profiling measurements that we're actually, doing as part of our implementation. You'll notice that this is one area where Realm actually uses C++ exceptions. So we're actually going to wrap the execution of this task inside of a try block, right? And the reason for this exception is it's possible to, effectively toss an exception inside of Realm to effectively cancel the task as it's running. Right, you can effectively cancel the task while it's in the middle of running, and that is done using exceptions. So we wrap the execution of this task inside of a try block and catch any exceptions that are going to pop out. And if we do catch an exception, right, then we can effectively, we can say that this task was terminated and give the error code and details of like effectively like what the exception was that actually caused this task to be executed unsuccessfully, right? But importantly, you run your perf counters and then you call this execute task method on the processor impl and give it the name of the function ID associated with actually executing this particular task, as well as the raw argument data, the buffer of bytes with the size that you're actually going to pass to that task. So if we go look in processor impl, we can actually find that execute task call. Here we go, local task processor. Right, so here's that function ID and your buffer of bytes with your argument. I may ignore most of the stuff because the common case is to come in here and you take your reader-writer lock on the table of function IDs mapping to function pointers. You're going to look up this, an iterator into that table, and you can ignore probably most of this case, like it says here. I think we've mostly gotten rid of this stuff. This is a very old comment. Even refers to old Legion high-level runtime, which is gone. So. The common cases were down here. We actually pulled off our entry into this task table. Notice you can actually because this is a table, or because it's a standard map, right? The iterator is we don't ever delete things from this task table in Realm. So like once you found it and traversed it, right, you can release the lock and then you can still use the iterator because iterators are valid even under insertions in maps and stuff like that, right? So we can read that out. We have a little logging statement here, and then here's the magic where we actually dereference the function pointer and actually call the function pointer with all of the data needed to pass to the application or the Realm client to actually run this task, right? And so that's actually where we this is where control pops back out to the user to actually execute this task once it's ready to run. Okay. So that was a lot of stuff, but we made it all the way from the task spawn, all the way through to the point where we actually dispatched with our function pointer control back to the user to actually execute that task, right? And then once the user control returns from this function call, right, then we unwind all of the stack and stop our perf counter, stop our operation, mark that this task executed successfully, and so forth. Now, there's one way that I do want to mention here in the last 10 minutes, just to say there's one way in which this task can preempt itself, right? And that is that Realm will never actively preempt this task, right? This function pointer invocation here should actually run all the way from start to finish. In a perfect world, it would actually execute all the way through and then return and be done, right? But there's one way that you can actually preempt a task, and the user has to preempt a task, and that is by calling wait on an event. So let's actually take a look at that and actually see just what happens when we call wait on an event. And we'll see how much of this we can actually get through here. Okay, there's event wait. It actually calls wait fault aware. Right, which here's wait fault aware. We'll skip the case where there's no event. We get the generational event for this, right? Assuming it hasn't triggered, right? There's an early out here. If in case this is already triggered, right? Then we're immediately done, right? Let's see here. So if we're doing any kind of profiling measurements inside of the task for waiting on an event, right, we'll actually start to record those, right? And you can do this, this is actually looking up that thread local variable associated with, that we set, before we started running our task. So we can actually get the name of our thread that we're actually executing in here. This is just recording all of the wait. But then, you can actually get this call here to wait for condition, right? And this event triggered condition, right, it's actually going to be something that's going to say, let's actually look up what that actually looks like. Oh, is it not in here? Maybe it's in a, let's see if I can remember where that is. Event triggered condition. Did I not misspell it? It might be over in thread. I wonder if it's in threads.h. Nope. Huh. Okay, I might have to find that one later for you guys. But what this should be is this should actually be a well, actually we can go look for wait for condition and actually find the type for this. Let's see here. let's see, threads.cc. Oh boy. Okay, so this is clearly the part where I didn't study enough. I wonder if it's in tasks. Nope. Goodness. Okay, so I've clearly lost my memory of where this actually goes to. Maybe it's in, I wonder if it's in threads.impl or threads.inline. Yeah. Yeah, here we go. Okay, yeah, that's why I was losing track of things. Okay. All right, so this is a templated method, which is why it goes in threads.inline. But effectively, what event wait for condition is going to do here is effectively it's going to end up preempting this thread until this particular event precondition has triggered, right? And so what you can see here is that, modulo, signals and other kinds of things, and so like these kinds of things, right? We're actually going to tell the thread that it's going to sleep, right, to block on this particular event, right? Tell the thread scheduler that it's going to block, and this should actually block this particular thread until this particular thread waker condition has actually been satisfied. And so this actually will end up putting this task to sleep until this thread is actually ready to run again. Now, let's see, I forgot a little bit about how this works. I studied it last night, but I have lost my memory of how this actually, I think this thread blocking, I think thread blocking is actually the interesting method call here. So if we go into our threaded task scheduler, if we call thread blocking over here, yep, this is where we want to go. Right, so this is actually going to block this particular thread. Now what I'm missing is the part where I think, if I come back over here, I think this thread waker is actually going to register the condition, right, with the event impl as a waiter, and then look for a callback to effectively tell it to wake this particular thread up, right? This condition actually restores the condition, which is going to include the event that needs to trigger, as well as the thread to wake up once this task is ready to run again. Yeah. And so this is actually the part where we're actually doing the blocking of the thread, which will then allow other threads to actually start running, right? So this doesn't know about the event, right? This is just putting this thread to sleep. I think this event waker here, or this thread waker here, is what's actually going to register itself with this condition. Let's see if a thread waker is in here. Right, so this inherits from this particular condition callback, right? And effectively, what callback did we use over here in event impl to actually event impl over here? Yeah, event triggered condition, which actually might be, I wish I knew where event triggered condition, that would actually tell us a lot. But this is what's actually going to register itself as an event waiter with the event. And then it gets included in this condition, right? This condition callback, right, to actually remember which thread to actually wake up once that event has triggered. So when you get the event trigger, that will then signal this thing, which will then signal this thread waker, which will then wake up the thread and then allow it to start running, or at least tell this thread scheduler that this thread is ready to run again, right? Effectively, it's one of those resumable threads in the threaded task scheduler. And so that's how users can actually preempt their tasks by waiting on an event, and that will end up triggering this whole song and dance to actually make it so that the task goes to sleep when the user has to wait an event, and then wake it up again once the event has been satisfied. Okay, so I think I hand wave a little bit there. If you guys look at this code and get confused, I'll help you work through it offline. But effectively, that's how you end up putting tasks to sleep by waiting on events, and that notifies those threaded task schedulers, that the thread has gone to sleep, and therefore you can either start running a new task or what have you. Okay, So with that, I think I'm going to stop for today. If there are questions, let's take a few minutes here to handle those before the end. But otherwise, I think I'm going to call it quits here today.
I have one more question about last time. I couldn't find the recording of the previous session.
Yep. So it should all be on YouTube on the Stanford Legion channel.
Okay.
I'll send the link to you offline. But if you go to the Stanford Legion YouTube channel, I've been uploading all of the recordings onto YouTube. So yeah.
Okay. And if we have a question about this one, should we ask the question in the Teams chat, or where is the proper channel to ask questions?
I think anywhere in Slack would be fine.
Okay.
Just so everybody can see the answers, right? Like do it on one of the general channels. Like either if you want to ask a Realm question, ask on Realm Dev. If you want to ask a Legion question, ask on Legion Dev Core or whatever. I'll be happy to answer there so everybody can see the response. But I'm also happy to take questions here in this particular meeting too, if you want to.
Okay, maybe a couple of short ones. Why not using functors? Why using function pointers?
Yeah, so I think it's a little. So you're referring to like standard function, like why not use standard function?
Yeah, I noticed function pointer instantiation. Typically, functors are better.
Yeah, I think like there was a point where, and you'll see this a lot in Legion Realm, where we weren't allowed to use C++11, right? So like we had to support older supercomputers and stuff that didn't allow or didn't have C++11 compilers, right? And so there's lots of stuff in Legion and Realm that can be modernized, with like standard function instead of function pointer, right? To actually, use more modern C++ that will make things a little more ergonomic and stuff. And it's just a matter of like investing the time to actually do all those refactorings. I don't think there's any real good fundamental reason to use a function pointer versus like standard function.
Okay. Yeah. All the concurrency primitives, locks, mutexes, condition variables, atomics, threads, those I assume are adapters to existent multi-threading libraries so that they can be plug and play.
I would certainly think that you could certainly implement some of Realm's so certainly like threads, like we didn't actually go look at the thread implementation, but it backs onto like POSIX threads on most Linux systems and Darwin, but something different for Windows. Right. And with like Realm actually does roll its own locks using like C++ standard atomics and stuff, because we have found them to be faster and less reliant on OS level locks. Like POSIX locks tend to fall back to futexes, pretty aggressively, and that can be pretty slow. And so Realm has rolled its own locks. Now, if you want to try and make one that's faster, I don't think we would be opposed to that, but I think you'd be hard pressed to actually improve on like the auto lock that Sean has got in here already. So yeah, but certainly like those interfaces are general, right? The idea is that we're actually trying to, one of the things that you'll actually notice in this whole thing is like we're actually trying to eliminate the operating system entirely, right? Like this whole threaded task scheduler is doing the work that an OS might normally do, but doing it locally inside of the process instead of allowing the operating system to control all this stuff, right? So
nice.
One thing to note is that because of what Mike said about Realm by default only allowing one thread running per processor, if you can deadlock yourself if you try and use OS or pthread based like locks and stuff, because you're never going to be preempted, right?
You can. Like if you tried to use a pthread lock inside of a Realm task, you do have to be very careful about forward progress guarantees. Like Realm makes forward progress guarantees as long as all of your waits and blocks occur with Realm primitives. If you block on something that Realm can't understand, then certainly you can get yourself tangled up and lose your forward progress guarantees.
And then the user thread scheduler,
Yep.
out of economy and efficiency, I understand that it's avoiding more than one kernel thread. So what is there to schedule? If it uses its internal scheduler for some sort of cooperative threads, then maybe coroutines in C++20 would be an answer to that.
User level threading with tasks is equivalent to coroutines, but without relying on C++ coroutine, syntax and stuff like that. We literally are doing, like equivalents to like doing context switching on the user thread.
Nice.
Right, and swapping off the stack and stuff, and putting a new stack, binding a new stack to the thread, right, inside of Realm, right. So that I didn't show that part of the code where the the user thread scheduler actually does those context switches, but it is in there, and it does something very similar to what coroutines does under the hood of C++. It's just the syntax looks very different. We've done it with tasks instead of with coroutines.
Right. Well, I have two more questions, but I'll give other people a chance, and maybe I'll ask them later in a channel or something.
Well, you just want to ask them since no one else seems to have anything?
Yeah. So it's not clear to me the use of the priority. So if tasks are being run as they come, then where does the priority come into play?
Well, so you can accumulate a bunch of tasks, right, that are ready to run, but there's only one running at a time, right? So like each processor has it's executing one task at a time in the common case, right? But you may have a whole bunch of tasks that are ready to run, right? And so the priority effectively sets the order in which those waiting tasks appear in the queue, right? And so effectively allows tasks that are higher priority that might, have their event precondition triggered later to jump to the front of the queue, right? To be the next thing ready to run, even though their precondition event triggered later, right? So,
right.
Yeah.
And somewhat related. So is there like a producer-consumer paradigm for creating tasks and running them? Is a producer essentially creating tasks and then separately a consumer running them? Or there's no such separation.
Well, yeah. So in Realm, like all dependencies are expressed as event preconditions, right? So there's no like if there is a data dependence between two things, right? It's up to the client, the Realm client, to actually specify that. That in terms of a control dependence by passing, event preconditions between two tasks. So Realm actually doesn't know about data dependencies. Legion does, but Realm doesn't. Realm just sees control dependencies. But the thing is, it's not like a strict producer consumer kind of thing, right? One task can produce output that gets fed into end consumers, right? Right, or a consumer might consume from multiple producer tasks, right? And so Realm doesn't encode that explicit producer-consumer relationship. It just says here's the one event precondition that needs to trigger before this task runs, right? And it's up to the client to say, to create those relationships between the tasks.
All right, that makes sense. Thank you.
Yep. Okay. Any other questions for today? If not, next week will be a Legion week. All right. Well, thanks everybody. And I will upload this on YouTube, just like the last few, and have the recording available for everyone. See you next week.
Thank you.